we now want to consider improper integrals, that is, integrals over infinite regions. For instance, we want to ask, what does it mean to take the integral of a function from a to infinity? So for instance, geometrically, that would mean a problem such as looking underneath the curve y equals 1 over x squared and asking about the area of this region from 1 all the way to infinity. And asking, is this region finite or infinite? Of course, the fundamental question is, how do we even define the area of an infinite region? Well, having done calculus for a little while, I'm sure you'll be expecting the answer is to be as the limit of the area of finite regions. So what do? We look at the curve y equals 1 over x squared and we find the area from 1 to t. Well, an easy calculation tells us that that area is 1 minus 1 over t. So the area from 1 to 2 is a half, from 1 to 3 is a 2/3, from 1 to 4 is 3/4, etc. And as t goes to infinity, this area tends to infinity. So it makes sense to say that the integral from 1 to infinity of 1 over x squared should be the limit as t goes to infinity of the integral from 1 to t. Let's have a look at the calculation that yields this picture here. So the antiderivative of 1 over x squared is minus 1 over x. So we're looking for the limit as t goes to infinity of minus 1 over x between 1 and 2. We evaluate that, we get minus 1 over 2 minus minus 1, so plus 1. So we get this region, the integral from 1 to t has value 1 minus 1 over t, that's this area we discussed. And if we take the limit as t goes to infinity of that, I think we can all see that that's going to be equal to 1. So let's look at the general definition. Whenever we have a function f such that the integral from a to t exists for all t greater than or equal to a, then the definite integral enables us to kind of define a function of t to be this integral, and we can then take the limit as t goes to infinity of that value. And so we will define this improper integral, the integral from a to infinity, to be this limit if it exists and is finite. And similarly, we can do the same thing on the left-hand side. We can define integrals from minus infinity to a as the limit as t goes to minus infinity of the integral from t to a. And obviously, again, we'll need, as a hypothesis, to assume that this thing exists so we can take the limit. And again, if this limit exists and is finite, then we'll call that the value of this improper integral. And we'll say that these improper integrals are convergent if these limits are finite and divergent if the limit is infinity or it doesn't exist. Let's have a look at another similar example to the one we started with, the integral from 1 to infinity of 1 over x. So now, according to our definition, that's the limit as t goes to infinity of the integral from 1 over t, 1 over x dx. So that's the limit as t goes to infinity of log x evaluated between 1 and 2, 1 and t. So that's log t minus log 1, which is 0. So it's just the limit as t goes to infinity of log t, which we know is infinity. So this gives us a similar picture to the one that we had for 1 over x squared. To the naked eye, these functions look kind of similar. But in this case, the area is actually infinite, whereas when we took the function 1 over x squared, actually the curve was below this, and the area turned out to be precisely 1. So clearly we can't answer this question of convergence or divergence using the naked eye. We have to do these calculations. Let's look at another classic pair of examples. E to the minus x. Again, this has a asymptote onto the x-axis as x goes to infinity, a horizontal asymptote. So it's natural. This is a natural candidate for a finite improper integral. So this is defined as the limit as t goes to infinity of the integral from 0 to t. The antiderivative of e to the minus x is minus e to the minus x. We want to evaluate that between 0 and t. When we do that, we get negative e to the minus t, negative negative 1. So that's minus e to the minus t plus 1. As t goes to infinity, this thing tends to 0, just yielding 1. So again, the area under the curve e to the minus x from 0 to infinity rather neatly turns out to be exactly 1. Let's look at 1 over root x. Again, we'll go from 1 to infinity now because, of course, this is not defined at 0. So that's going to be the limit as t goes to infinity of the integral from 1 to t. The antiderivative of 1 over root x is 2 root x. So it's the limit of 2 root x evaluated between 1 and 2, which is the limit as t goes to infinity of 2 root 2 minus 2, which is, of course, infinity. The next thing we want to do is get some more general formulas. So we can ask in general about the convergence of 1 over x to the p, where p is positive. And this will include the 3 examples that we just looked at, as well as obviously infinitely many other examples. So it enables us to do the calculation once for many different cases. And we only consider the case p greater than 0. If p is negative, this is actually 1 over x to the p is actually a positive power of x, which is going to infinity, and so there's no chance that the integral will converge. So we can do this calculation. If p is not equal to 1, we can do this calculation in one go, because the antiderivative of 1 over x to the p is 1 over p minus 1, sorry, negative 1 over p minus 1 over 1 over x to the p minus 1. So we want to evaluate that between 1 and t. So we get this expression. Now we ask ourselves, what happens to 1 over t to the p minus 1 as t goes to infinity? Well, if p minus 1 is positive, this is 1 over a positive power of t, and a positive power of t is going to infinity, so 1 over it will go to 0. And so that will just leave us with a limit of 1 over p minus 1. So if p is greater than 1, this improper integral will converge to 1 over p minus 1. When p is less than 1, t to the p minus 1 will be negative. So 1 over that is actually t to the 1 minus p, which is a positive power of t, and that's going to go to infinity. So the integral will diverge when p is less than 1. So we get this answer to that question. Now we just have to throw in the case p equals 1, which is the separate calculation we did before, to get a complete answer. So remember that when we did this by hand, we found that it diverged. So putting this all together gives us this theorem for the convergence of the integral of 1 over x to the p from 1 to infinity. That it converges to 1 over p minus 1 if p is greater than 1, and it diverges to infinity if p is less than or equal to 1. So for instance, now if we have an example like 1 over x root x, we just have to notice that this is 1 over x to the 3 over 2, so it's exactly an example of this formula. P here is 3 over 2, which is bigger than 1, so according to this theorem, it'll converge to 1 over 3 minus 3 over 2 minus 1, which is 1 over a half, or 2. So that's how we do integrals from a to infinity, or from minus infinity to a. Let's have a look at another case where the function is defined over the whole interval from minus infinity to infinity, and we want to ask whether the integral, whether we can have a value for the integral from minus infinity to infinity. So again, this will only really make sense when we have like bell-shaped curves where the function f has a horizontal asymptote onto the x-axis in both directions, both left and right. So what do? We say that this doubly infinite improper integral converges if we can find an a such that both the integral from a to infinity and the integral from minus infinity to a converge. And in that case, we say that the value of this is the sum of these two things. And it's easy to see that in this case, it doesn't matter which a we choose. We'll get the same answer whatever a we choose. So let's have a look at an example. The integral from 1 over 1, the integral from minus infinity to infinity of 1 over 1 plus x squared. Remember, that's one of these bell-shaped curves with horizontal asymptotes in both directions. Let's do the calculation from 0 to infinity. It's the limit as t goes to infinity of the integral from 0 to t, which is the limit as t goes to infinity of arctan x evaluated between 0 and t. And the arctan x evaluated between 0 and t is arctan t minus arctan 0. Arctan 0 is 0. And as t goes to infinity, arctan tends to pi over 2. So we get that the area under this curve from 0 to infinity is pi over 2. And then if you remember the symmetry of this curve, you'll expect to get the same answer in the other direction. And we indeed do. Let's look at that calculation. The integral from minus infinity to 0 of 1 over 1 plus x squared is the limit as t goes to minus infinity of the integral from t to 0. So it's the limit as t goes to negative infinity of arctan x evaluated between t and 0. So that's arctan 0 minus arctan t. And arctan 0 is 0. And as t goes to negative infinity, arctan t tends to negative pi over 2. So the two negative signs cancel out, giving us a plus pi over 2, as we expected. So putting this all together, both one-sided improper integrals converge to pi over 2. So the integral from minus infinity to infinity is going to be the sum of these two things, which is pi over 2 plus pi over 2. So that gives the remarkable answer that this area under the curve 1 over 1 plus x squared between minus infinity and infinity turns out to be exactly pi. So this is one kind of improper integrals. There's another kind where our function has a vertical asymptote, and we'll consider that kind of integral in the second part.